This video is sponsored by Brilliant. Imagine an element so rare and elusive that it became the last natural occurring piece of the periodic table to be discovered. With atomic number 75, rhenium wasn't identified until the 1920s, long after the periodic table had already been established. Its late discovery wasn't because scientists weren't looking for it, but because rhenium hides deep within the Earth, existing in only trace amounts. This silvery white metal was the final missing link among the stable elements, predicted to exist for decades, yet stubbornly refusing to reveal itself. Welcome to Cube Chemistry, where we will discuss all the elements of the periodic system and also do experiments. So if you like this video and want to see more, make sure to like, subscribe and hit the notification bell so you will never have to miss another episode. Also, make sure to fill in the poll in the post section of the channel. For next week, we will also be discussing another element again. Now, inside this cube lies one of the rarest elements on Earth, rhenium. At first glance, it may look simple, a small silvery lump, but look closer and you see the subtle texture of a dense metallic surface that seems to be almost glowing under the light. The metal appears to be smooth, yet grainy, reflecting with a soft platinum-like sheen. Now, though it might look ordinary, this tiny sample is astonishingly heavy for its size. If you could hold it in your hand before it was sealed in the acrylic, you'd feel its weight immediately. Rhenium is one of the densest elements known, over 20 times heavier than water, giving it a satisfying sense of gravity and substance. Okay, so it is dense, but can you lick it? In its pure metallic form, rhenium is considered chemically stable and largely non-toxic. We also see this in the periodic licking table. Unlike heavy metals such as mercury, cadmium or lead, rhenium doesn't easily dissolve, oxidize or react with moisture or acids under normal conditions. Now that means a clean, solid piece of pure rhenium metal won't release harmful ions or fumes. It simply sits there, inert and shiny. In laboratory handling, rhenium metal is generally classified as safe to touch, and it doesn't corrode or leach into the environment easily. Now, safe in the chemical sense doesn't make it edible or hygienic. Any unsealed metal sample could carry dust, machining residues, or trace contaminations from production, which could be unhealthy to ingest. The metal's density also means that it could contain sharp edges or microscopic particles that might scratch or irritate the mouth. So, while rhenium itself is not chemically dangerous, it's still best admired behind glass or in acrylic, perfectly safe, beautiful and untouched. The existence of rhenium was actually predicted decades before it was found. In 1869, Dmitri Mendeleev created the periodic table and noticed there were gaps for undiscovered elements. One gap was for an element with the properties similar to manganese, which would have atomic number 75. Chemists refer to this hypothetical element as AK manganese, or sometimes DVI manganese, indicating it was one or two places down from manganese. For years, scientists searched for this missing element in various minerals without success. It was a bit like a treasure hunt for a nearly invisible prize. In the 20th century, a Japanese chemist named Masataka Ogawa thought he had found the elusive element. In 1908, Ogawa announced that he discovered a new element and named it Nipponium, and P in honor of Japan. Now, he believed this was element 43, another missing element, but in fact, the sample he had was element 75, rhenium. Ogawa had unknowingly found rhenium, but he misidentified it as the wrong element. Now, at the time, his results were not widely confirmed, partly because he published some findings in Japanese and because everyone was expecting element 43 and not 75. So it wasn't until many years later, just before Ogawa's death, that an analysis of his original sample showed it indeed contained rhenium. In hindsight, Ogawa was the first to lay hands on rhenium, but he didn't realize what he had. The official discovery of rhenium came in 1925 in Germany, when three scientists, Walter Nodak, his wife, Ida Take Nodak, and Otto Berg, conclusively identified element 75. They were systematically searching for both element 43 and 75, the two missing spots in the periodic table's transition metals. Using refined analytic techniques, including spectroscopy, they detected the signatures of a new element in several minerals. They found traces of rhenium in an ore of platinum, as well as in minerals like columbite, gadolinite, and molybdenite. Later in 1928, the Nodak team managed to extract about 1 gram of actual rhenium metal by processing an astonishing 660 kilograms of molybdenite ore, a testament to how dilute rhenium was in the material. The discovery was a milestone. Rhenium was the last stable, naturally occurring element to be discovered and identified on the periodic table. Now, the name rhenium was bestowed by the discoverers after Rhenus, the Latin name for the Rhine River in Europe. This was fitting as some of the ores they worked with actually came from the Rhine region. Interestingly, in the same 1925 announcement, the team also claimed the discovery of element 43, which they named Masurium, after Masuria, a region in East Prussia. However, their claim for element 43 could not be reproduced by other scientists. It turned out that element 43, technetium, has no stable isotopes and does not exist in nature in significant amounts. It was eventually first produced artificially in 1937. So rhenium, element 75, truly stands out as the last natural occurring element that science has uncovered. By the early 1930s, the periodic table roster of naturally present elements was essentially complete with rhenium's addition. All elements discovered after that point were either radioactive elements found in decay chains or synthetic elements created in laboratories. In the years following its discovery, rhenium maintained a laboratory curiosity for a while because it was so rare and difficult to extract. Early uses were limited and mostly for research. In 1928, that first gram of rhenium was reportedly sold for a very high price, around $10,000 per kilogram, a fortune at the time. For a couple of decades, rhenium wasn't produced in large quantities, and chemists continued to study its properties. It wasn't until the mid-20th century, with new technologies and a growing understanding of high-temperature materials, that rhenium started to find practical applications. By the 1950s and the 1960s, interest in rhenium surged as metallurgists and engineers developed rhenium-containing alloys. From that point on, rhenium transitioned from a scientific oddity to a strategic resource, especially as jet engines and industrial processes demanded materials that could withstand extreme conditions. Now, like mentioned before, rhenium's name has an interesting origin linked to geography. The element is named after the Rhine River, one of Europe's great rivers. Rhenium comes from Rhenus, the Latin word for the Rhine. Walter and Ida Nodak chose this name in 1925 when they confirmed the element's discovery. Why name an element after the Rhine? One reason is that the first samples of rhenium they isolated were derived from ores found in the Rhine Valley region. By naming the new element after the river, the discoverers gave a nod to the location that contributed to their find. Naming an element after a river is somewhat unusual. Many elements are named for countries, cities, mythological characters, or famous scientists. In the early 1900s, it was common for discoverers to propose names reflecting national pride or geographic connection. For example, element 32 was named germanium for Germany and element 84 polonium for Poland. In the Nodak's case, they could have named element 75 after themselves or their homeland, but they opted for a more modest tribute, the local geography. The Rhine River flows to Germany, and it was a meaningful landmark near their research. The name rhenium thus roots the element in a sense of a place. It is worth noting that Masataka Ogawa's earlier name for what turned out to be rhenium, nipponium, after Japan, did not survive in the periodic table. Once the Nodak's discovery was confirmed and accepted by the scientific community, the element officially entered the periodic table as rhenium. Now, rhenium is a metal with remarkable physical properties, and we're going to repeat ourselves a little bit, but it's extremely dense, more than 20 times denser than water. In practical terms, a small chunk of rhenium feels really heavy for its size, similar to how a piece of platinum or gold would feel. In fact, rhenium is one of the densest metals, slightly less dense than platinum, iridium, or osmium, but denser than almost anything else. Now, rhenium is also very hard. On the Mohs hardness scale, it's around a 7. For comparison, quartz crystal is a 7 and hardened steel is in a similar range. This hardness means rhenium can resist scratching and wear quite well. The metal has a crystalline structure known as a hexagonal close packed, which is a tightly packed arrangement of atoms. This contributes to its strength and hardness. Rhenium in bulk form is fairly ductile, especially if it's been annealed, slowly cooled after heating. An annealed piece of rhenium can be rolled into foil without cracking, which is somewhat surprising given its hardness and high melting point. Speaking of melting point, rhenium has one of the highest melting points of any element. It doesn't melt until about 3180 degrees Celsius, approximately 5750 degrees Fahrenheit. Only tungsten's melting point is higher among metals. Carbon sublimates around 3600 degrees Celsius, but it doesn't have a normal melting point at atmospheric pressure. Rhenium's boiling point is also extreme, nearly 5600 degrees Celsius. Now these numbers are mind-boggling. Such temperatures don't occur naturally on Earth, except perhaps in lightning bolts or small spots in nuclear explosions. Essentially, rhenium remains solid under conditions that would turn most metals into a liquid or gas. Chemically, rhenium is very versatile, yet generally not highly reactive in everyday conditions. It is a transition metal, and in terms of chemistry, it is akin to manganese and technetium, its neighbors in the periodic table, group 7. At room temperature, rhenium does not tarnish or rust rapidly in air. It forms an oxide layer only very slowly, so a piece of rhenium metal will stay shiny for a long time. It's stable in water and doesn't react with plain water or humid air under normal conditions. Only in the presence of strong chemicals or high heat does rhenium show more reaction. For instance, rhenium will resist attack by common acids like hydrochloric or dilute sulfuric acids when cold. Even the famously aggressive aqua regia, a mix of nitric acid and hydrochloric acid that dissolves gold, has little effect on rhenium at room temperature. However, if you heat rhenium in concentrated nitric acids or other oxidizing acids, it will eventually react. When rhenium metal is strongly heated in air or oxygen, it forms a yellow oxide, rhenium 7 oxide, which is volatile, meaning it turns into gas and can evaporate. This oxide readily dissolves in water to form perrhenic acid, an acid solution containing rhenium. That trait is actually useful, as we will see, for extracting rhenium from ores. One striking feature of rhenium is the wide range of compounds it can form. Rhenium can exhibit many oxidation states, from as low as -1 in certain complex molecules, all the way to +7 in its highest oxidation state in perrhenate compounds. The most common oxidation states of rhenium in compounds are +7, +4, and +3. The +7 state, for example, rhenium forms compounds like perrhenates, similar to how manganese forms permanganates in +7. In lower oxidation states, rhenium can form interesting complex compounds, often with multiple rhenium atoms bonded together. Rhenium has a tendency to form metal-metal bonds in some of its chlorides and other complexes. Without diving too deep into the organic chemistry, it suffices to say rhenium's chemistry is rich. Salts like ammonium perraphenate are common commercial forms of rhenium. They are white, water-soluble solids from which rhenium metal can be obtained. Overall, while elemental rhenium is quite inert in daily circumstances, in compound forms it can participate in a variety of chemical reactions, acting as catalyst or forming coordination complexes. A quick note on the atomic structure and isotopes. Rhenium atoms are quite large. As a third-row transition metal, it has lots of electrons. Naturally occurring rhenium is composed of two isotopes, rhenium-185 and rhenium-187. Rhenium-185 is stable, does not decay, and makes up about 37% of natural rhenium. Rhenium-187 is actually slightly radioactive. It has an extremely long half-life, around 41 billion years. This half-life is many times longer than the current age of the universe. So for all practical purposes, Rhenium-187 is stable in our experience. It decays so slowly that its radioactivity is negligible. A chunk of rhenium metal emits only a tiny amount of radiation. Now, for these reasons, we consider rhenium a stable element, and its two isotopes sit safely together in the metal. Scientists can even use the rhenium-187 decay, which turns into osmium-187, as a method for dating very old rocks. That's known as rhenium-osmium dating. But if you were holding rhenium or using it in an application, you wouldn't notice any radioactivity. It is safe to handle in metal form as it doesn't easily react or pose a toxicity hazard in its elemental state. Rhenium is ultra rare in the Earth's crust. To give an idea, it is estimated to average about only 1 part per billion in crustal rocks. That makes it one of the least abundant elements in the Earth's continental crust, roughly the 77th most abundant element. Now, in comparison, even gold, which we think of as very scarce, is about 4 parts per billion in the crust. Rhenium is rarer than gold or platinum in the Earth's crust, and because of this, rhenium does not form ridge ore deposits of its own. You won't find a rhenium mine where the ore is full of rhenium. Instead, rhenium is typically found as a trace impurity within other mineral ores. It's usually associated with molybdenum minerals. The primary source of rhenium is the mineral molybdenite, molybdenum disulfide, which often contains tiny amounts of rhenium in place of some molybdenum atoms. A typical molybdenite ore might have only 0.001% to 0.2% rhenium. Occasionally, geologists have found molybdenite with unusually high rhenium content, in rare cases up to 1% or so. But those are exceptions. Interestingly, for a long time, no mineral composed of primary rhenium was known to occur naturally. It was only in the 1990s that geologists discovered a rhenium mineral in nature. In 1994, a new mineral was found at the Kudryavy volcano on the Coral Islands, far eastern Russia. It was a rhenium sulfide mineral with the following formula. This mineral was named rheniite. It forms when volcanic gases rich in rhenium cool and deposit in tiny crystals. The Kudryavy volcano was found to emit a fumarole gas containing rhenium, which then condenses as rheniite. This was a remarkable discovery. Imagine a volcano smoking out rhenium in the form of a mineral. However, rheniite is extremely rare and not an economic source. The volcano might release only a few tens of kilograms of rhenium per year. It's of interest mostly to mineral collectors and scientists. In practical terms, virtually all the rhenium we use is obtained as a byproduct from mining other metals, especially copper and molybdenum. The largest supplies of rhenium come from porphyry copper deposits that also contain molybdenum. Places like the great copper mines of Chile, for example the Chuquicamate and the El Teniente mines, have molybdenite in their copper ore, and that molybdenite contains rhenium. Chile is known to have the world's largest rhenium reserves and is often the top producer of rhenium. Other significant producers include the United States, where large copper molybdenum mines are in states like Utah, Arizona, and Nevada. Other countries are Peru, Poland, and a few other countries with big copper molybdenum operations. When these mines process ore to extract copper and molybdenum, rhenium comes along for the ride. The typical process, molybdenum is extracted from copper ore as molybdenum disulfide concentrate. To get molybdenum metal, the concentrate is roasted in air, heated strongly so that converts to molybdenum oxide and sulfur gases. During this roasting, the rhenium present in the molybdenite also oxidizes. Rhenium turns into rhenium-7 oxide, which, unlike molybdenum oxide, is volatile. The rhenium oxide becomes a vapor and exits with the exhaust gases from the roaster. This might sound like we're losing the rhenium, but in modern operations, those gases are carefully captured. The rhenium-rich flue gas is passed through scrubbers or other systems where it dissolves in water, forming a solution of perrhenic acid, essentially rhenium in a form that stays in liquid. Now the rhenium is in a liquid solution. This next step is to isolate it as a solid compound. Typically, the solution is treated with chemicals like ammonium or potassium chloride, causing rhenium to precipitate as a salt, ammonium perrhenate. Ammonium perrhenate is a white crystalline salt that contains rhenium. It can be filtered and purified by recrystallization to a high degree of purity. This salt is the main intermediate that is sold or transported, often referred to as APR, ammonium perrhenate, in the industry. Finally, to get metallic rhenium, ammonium perrhenate is decomposed at a high temperature in a stream of hydrogen gas. In this reduction process, the hydrogen reacts with the oxygen in the compound and leaves behind pure rhenium. The reaction is typically written like this. Now what comes out is rhenium powder. Rhenium metal is often traded or shipped as a gray powder. It can be consolidated by pressing and sintering into larger solid pieces if needed. But even as a powder, it is a useful form for alloying with other metals or making into pellets. Because rhenium is only obtained as a byproduct, its annual production is quite limited. Worldwide, mining operations produce on the order of only 40 to 50 tons of rhenium per year. To put that in perspective, humans mine around 20 million tons of copper each year. So rhenium is literally 1,000,000 times less produced than copper. Even gold production on the order of 3,000 tons per year globally dwarfs rhenium. We're talking about a few dozen tons of rhenium in the whole world annually. Additional rhenium, perhaps another 10 to 20 tons per year, is recovered by recycling. For example, recycling used catalysts that contain rhenium or recycling superalloy scrap from turbine blades. Given its rarity and the growing demand in specialized industry, rhenium has been classified as a critical or strategic material by many governments. Supply depends on the production of other materials. If copper or molybdenum output drops, rhenium supply can be affected. This scarcity is reflected in rhenium's price. Rhenium is quite expensive. It has historically been one of the priciest industrial metals, excluding precious metal like gold or platinum. In the mid-2000s, as demand for jet engine alloys and reforming catalysts grew, rhenium prices soared. At one point, around 2008, rhenium cost over $10,000 per kilogram. That is about $10 per gram, which is several times the price of silver, for example. Prices have fluctuated since then. As more recycling came online and demand leveled, the price fell to a few $1,000s per kilogram. But it's still costly. Think on the order of thousands of dollars for a coffee mug weight of rhenium. Rhenium might be rare, but it punches above its weight in terms of applications. Many advanced technologies rely on a pinch of rhenium to function. Here are the major ways rhenium is used. The single biggest use of rhenium today is in high-temperature alloys, especially nickel-based superalloys, used for turbine blades and jet engines and industrial gas turbines. About 70% of all rhenium produced goes into these alloys. Jet engine parts, particularly the turbine blades and the vanes that operate in the hottest part of the engine, need to withstand extreme temperatures and forces without deforming. By adding a small percentage of rhenium, typically 3 to 6%, to nickel-based alloys, metallurgists found that the alloy's creep strength, its ability to resist slow deformation under high heat and stress, is greatly improved. In essence, rhenium strengthens the alloy at high temperatures, allowing engines to run hotter and more effectively. For example, second-generation single-crystal turbine blade alloys contained about 3% rhenium, and third-generation alloys ramped that up to around 6% rhenium. This allowed military jet engines like those on fighter jets and later commercial jet engines to achieve higher thrust and fuel efficiency. The F-15 and the F-16 fighter jet engines use 3% rhenium alloys, while newer models like the F-22 Raptors engines move to 6% rhenium alloys. Even some land-based power turbines use rhenium-containing superalloys for better performance. However, because rhenium is so scarce and expensive, engine manufacturers constantly seek ways to minimize its use. Newer alloy generations have added other elements like ruthenium in place of rhenium to reduce the required rhenium content. Additionally, recycling programs retrieve rhenium from old turbine blades. Still, rhenium remains a critical ingredient for the hottest sections of modern jet engines. Every time you fly in a jet aircraft, there's a good chance that a bit of rhenium in the jet engine alloy helps keep you aloft by enabling the engine to handle the heat of the combustion. The second major application of rhenium is in the chemical industry as a catalyst, particularly in the petroleum refining. A catalyst is a substance that speeds up the chemical process without being consumed. Rhenium is used in combination with platinum to create highly effective catalyst for a process called catalytic reforming, sometimes specifically termed rheniforming when rhenium is involved. This process takes low-octane petroleum naphthas, straight-run gasoline from crude oil, and converts them into high-octane gasoline compounds. Essentially, it helps to make better gasoline, especially important when leaded gasoline was phased out and refineries needed to boost octane without using lead additives. Platinum on its own is a good reforming catalyst, but adding rhenium improves the catalytic's lifespan and tolerance. Rhenium platinum catalysts, typically 0.3% rhenium or so on a silica alumina base, are more resistant to poisoning by impurities like sulfur, nitrogen, phosphorus compounds in the feedstock. These impurities can deactivate other catalysts, but rhenium makes the catalyst robust. This means the catalyst can be used longer and under more stressful conditions, improving efficiency. By the 1970s, many refineries worldwide had switched to PTRE reforming catalysts for producing high-octane lead-free gasoline, which was crucial for reducing air pollution and enabling catalytic converters in cars. Even today, a significant portion of rhenium consumption, perhaps around 10 to 15%, goes into catalysts for making gasoline and other petrochemicals. Another catalytic use of rhenium is in olefin metathesis, an important reaction in organic chemistry. Rhenium-7 oxide on alumina is one catalyst for that process. Additionally, rhenium catalysts are used for hydrogenation in fine chemical production. Their resistance to poisoning makes them valuable for reactions where other catalysts would be ruined by trace contaminants. In summary, rhenium helps make your car's fuel and many other chemicals by enabling more durable catalysts. Rhenium is often mixed with tungsten or molybdenum to improve their properties. Tungsten by itself is another very high melting metal. Tungsten melts at around 3422 degrees Celsius. By adding rhenium to tungsten, for instance 5, 10 or up to 25% rhenium, the resulting tungsten-rhenium alloy becomes more ductile and less brittle, especially after being heated. Pure tungsten has a tendency to become brittle after recrystallization, but tungsten-rhenium alloys stay together. This makes them easier to machine and form, and also more resilient during thermal cycling. Now, these alloys also maintain excellent strength at high temperatures. One important use of tungsten-rhenium alloy is in thermocouples, devices that measure temperature. A specific thermocouple type is made from a wire of tungsten with 5% rhenium paired with a wire of tungsten with 26% rhenium. This combination, called Type C thermocouple, can measure extremely high temperatures up to 2200 degrees Celsius, far beyond what platinum thermocouples can handle. Such thermocouples are used in jet engine development, rocket engines, and scientific furnaces, anywhere you need to measure very high temperatures accurately. Tungsten-rhenium alloys are also used for X-ray machine components. In many X-ray tubes, the target anode, which is struck by electrodes to produce X-rays, is made of tungsten with a small percentage of rhenium, for example 5 to 10% rhenium. Now, this rhenium helps the tungsten to withstand the intense heat and shock of the electron beam. It improves the anode resistance to cracking and pitting during the repeated use. This is why some medical and industrial X-ray tubes advertise tungsten-rhenium targets. They last longer and can handle higher power loads. Similarly, certain high-power light bulbs or filament lamps have used tungsten-rhenium wire to increase lifespan or performance under extreme conditions. Rhenium's ability to withstand heat and arc corrosion make it valuable in some electrical components. Electrical contacts, switch contacts, relay points, etc. that experience arcing can be made with rhenium or rhenium alloys. When an electrical contact opens or closes under load, an electric arc can form, which often oxidizes and damages the contact surface over time. Rhenium has an interesting advantage. Its oxide is volatile and will evaporate at roughly 360 degrees Celsius. So if an arc forms an oxide and a bit of rhenium on the contact surface, the resulting oxide can essentially vaporize away, leaving a clean metal surface behind. In effect, rhenium contacts can self-clean to a degree, maintaining good conductivity longer than some other metals in harsh switching conditions. Now this makes rhenium useful for contacts in certain high-performance switches and systems where reliability is crucial and maintenance is infrequent. Rhenium also finds use in filaments and wires for specialized lamps and instruments. One example is in mass spectrometers and ion gauges, devices used in scientific research and vacuum systems to measure gas composition or vacuum pressure. These instruments often use a hot filament to emit electrons or ions. Rhenium wire filaments are favored because they can operate at red-hot temperatures for long periods and are less prone to burnout. Unlike plain tungsten filaments, a rhenium filament tolerates exposure to a small amount of residual gas without oxidizing and breaking immediately. An area where rhenium has made a niche for itself is in nuclear medicine. Certain isotopes of rhenium are radioactive and can be used for cancer treatment. Specifically, rhenium-186 and rhenium-188 are two isotopes employed in what's known as radiotherapy. These isotopes emit beta radiation, which can destroy cancer cells. They have been used in treating liver cancer, for instance by injecting a rhenium-containing radiopharmaceutical that targets tumors and delivers lethal radiation directly to them. Rhenium-188, with a half-life of about 17 hours, has also been explored for treating pancreatic cancer by linking it to molecules that seek out cancer cells. Another application is in treatment for skin cancer. Rhenium-188 can be incorporated into a small device to paste or treat basal cell carcinoma or squamous cell carcinoma on the skin surface. The beta particles it emits only penetrate a short distance, killing the tumor cells without deeply harming surrounding tissue. Rhenium-186, half-life 3.7 days, is used in some therapies for pain relief, bone cancer metastasis, and other internal cancer treatments. One reason rhenium is chosen is that it chemically behaves similarly to technetium, an element widely used in diagnostic nuclear medicine, like the isotope technetium-99m in scans. Rhenium's chemistry allows scientists to attach it to the same kind of biological targeting molecules, but rhenium isotopes can be longer lived and are therapeutic. Technetium-99m is a gamma emitter for imaging, while rhenium-188 is a beta emitter for therapy. In summary, tiny amounts of rhenium prepared in nuclear reactors or generator systems are saving lives by helping to destroy cancer cells in a controlled way. Rhenium's high-performance characteristics make it valuable in some cutting-edge applications. In the aerospace industry, beyond its role in jet engine blades, rhenium is used in rocket engines and thrusters. Some high-performance rocket thrust chambers and nozzles, for example in satellite propulsion and upper-stage rocket engines, have been made from rhenium or rhenium-coated materials. A notable case is in satellite attitude control thrusters, where rhenium chambers can withstand repeated firing at a very high temperature without eroding. Rhenium's combination of strength at heat and resistance to combustion make it ideal for these small but critical rocket components. It has been reported that certain booster rocket engines and space nuclear power system have utilized rhenium in components to exploit its durability and ductility at extreme conditions. In the defense sector, rhenium is sometimes used in high-precision gyroscopes and guidance systems. Gyroscopes are devices that keep aircraft or missiles oriented. They often need components that are very dense and wear-resistant to spin smoothly and resist shock. Rhenium's density and stability make it suitable for parts in gyroscopes and accelerators that need mass and stiffness. From the above, it is clear that rhenium is a key enabling material in many domains. It's in the engines that fly airplanes, the catalysts that produce clean fuel, and the devices that explore space, and even in treatments that fight cancer. We only use tiny amounts, grams or kilograms, in each application, but those small quantities are often critical. There are few, if any, substitutes that perform as well as rhenium in the combination of extreme heat and chemical stress. process. Engineers and scientists value rhenium because it does what few other elements can do. The story of rhenium reminds us that breakthroughs aren't just about collecting facts, they're about connecting ideas, solving puzzles, and thinking like a scientist. Predicting a missing element required math, logic, and physical understanding. Explaining why rhenium has such a high melting point or how its atomic structure leads to unusual behavior calls for physics and math at their finest. That's exactly where Brilliant comes in. Brilliant is an interactive learning platform that helps you build those thinking tools through math, physics, and logical reasoning. Rather than memorizing formulas, you explore them. You'll solve problems that train you to think about how forces act, how energy flows, and how motion and structure connect. For instance, Brilliant offers a course like Physics of the Everyday, where you learn about the forces and kinematics using examples such as bikes, bridges, and water towers. Or their mathematical fundamental path helps you to get comfortable with number sense, algebra, geometry, and logic, the building blocks behind scientists predicting elements such as rhenium. So if you ever wondered why science works the way it does, not just what the answer is, Brilliant puts you in the driver's seat. If you're excited about understanding the world beyond just the elements on the periodic table, this is the perfect way to feed your curiosity. Don't let your brain get rusty. Galvanize your love of learning with Brilliant. To learn for free on Brilliant, go to brilliant.org and use this URL. You can also scan the QR code on screen or click on the link in the description. Brilliant's also given our viewers 20% off on an annual premium subscription, which gives you unlimited daily access to everything on Brilliant. In many ways, rhenium was the periodic table's lost missing piece, predicted by Mendeleev and finally found in 1925, closing an era of elemental discovery. All the while, its real-world importance was waiting to be realized. Today we see the importance in the roar of a jet engine, the flash of an X-ray tube, the precise measurement of a high-temperature furnace, and the hopeful treatment for certain cancers. We've learned that even an element so seldom seen can have an outsized impact on our lives. Now, we would like to thank the members that support our channel. Thanks for doing this. We really appreciate you. Now, if you think we missed anything, tell us in the comments. And if you want to know more about another element that treats cancer, take a look at this video about lutetium next.